Okay. Assalamu alaikum, everybody. My name is Mohammed Sami, and today we're doing a group presentation for our project in operating system subject. Our group members are me, Mohammed Sami, then we have Abdul Wafi, we have Amir, and we have Ahmed Khalid as well. We're going to start by the introduction, and who's going to start is going to be Amir. So go ahead, Amir.
Okay, so for the introduction, first, concurrency and synchronization are novel ideas in operating systems in contemporary computing. In case of shared resources, different processes or threads require coordination to prevent race conditions and maintain data integrity. This project aims at the implementation of a shared light switch system where several users compete to operate on a shared light switch using Peterson algorithm. So the Peterson algorithm is considered to be a simple and effective way in controlling the simultaneous usage of shared memory in the two process. It ensures mutual exclusion, progress and bounded waiting, and synchronization mechanisms. The project is also able to demonstrate solutions to critical section problems by using the basic operating system concepts through the integration of the algorithm on a shared light switch simulation. So next, for the problem statement, in environments like smart systems installed within a home, it is very common for multiple devices to attempt control over shared resources, like a light switch. When multiple users try to toggle the same light switch simultaneously, it can lead to inconsistent rate states or race conditions. This is why there is a need to ensure synchronized access, as neglecting to do so will cause unpredictable behavior. So a solution to address the challenge of ensuring concurrent access to a shared resource is by using Peterson algorithm. Peterson algorithm provides mutual exclusion, progress, and bounded waiting for two threads as opposed to traditional solution, making it a perfect choice for something like a shared light switch system.
Okay, thank you, Amir. Now we're going to move to the methodology with Ahmed Khalid.
Okay, I will talk now about the methodology. Uh, for this project, we made a simple system to show how two people or threads try to use the same light switch, which we followed simple steps. The first one, system design. Imagine there is a light that both users want to control. We use a shared variable to keep track of the lights is on or off. Both users have their own thread, and both can try to use the light at the same time. But to stop both from changing it together, which causes a problem, we need a way to control this. That's called mutual exclusion, making sure only one can access it at a time. About the synchronization and Peterson algorithm, we use Peterson algorithm to handle this problem. It used two things: flag to show if a thread wants to enter the critical section, the part where the light can be changed from on to off. Turn shows whose turn who turns to go in, who turns to go in, and how it's work. When a thread wants to enter, it sets the flag and gives the turn to the other thread. Only one thread can enter the critical section at a time. This way, only one person changes the light, avoiding any conflict or errors. About the implementation tools, we used JavaScript to make the system. We showed everything using console outputs, like whether the light is on or off and what the threads are doing. We don't use things like Mutex or smartphones because we want to show how to do it with just simple program using Peterson algorithm. This for the testing and validation. We test the system by making both threads try to change the light at the same time. We check the console output to make sure no race condition happen. Both threads change the light at the same time. Only one thread could access the light switch at time, like it's supposed to. For the project objective, we make a simple system where two threads act like they are like users trying to use a shared light switch at the same time. Use Peterson algorithm to make sure only one thread can change the light at any time. Show important concepts like important concepts like mutual exclusion. Only one at a time. Progress. Both threads can eventually do their work. Uh, Boundary waiting. No one waits forever. Proof that we can manage synchronization using only software logic, no metrics or smartphones. Smartphones, yeah, test the system and check that there are no race condition. For the related works, in operating system, when more than one processor tries to use the same thing at the same time, problem like race condition happen. That's why we use synchronize to avoid those problems. Only popular way to do the only popular way to do the Pearson algorithm made in 1981. It's a simple software method that lets two processes share resource without clashing. Many forms books talk about it, like operating system concept by separate Silver, books by Steelings and Tambion. Even though today's real system often use Mutix or smart force, Peterson algorithm is still great for learning how synchronization work using only software with no hardware tools needed. The original paper by Peterson also provides that this method works probably and follows all the rules for mutual exclusion. For the final thoughts, the project shows how two threads can safely share one resource, a light switch, using a simple but powerful synchronization methods. And this is for the related works.
Okay, thank you, Ahmed. For my part, I'm going to talk about the design and implementations. So the shared light switch system using the Bertrand's diagrams is actually a single page, single web page. We decided to do the backend using JavaScript and the front end using a simple HTML and CSS as well. For the system architecture, we use HTML as user interface, styling for CSS, and for the logic itself, we of course used JavaScript. We use it because it's simpler and better than C++ and a lot of other languages. So here is the HTML file. It's basically just a few texts with the title at the top and tables and headers as well, including the script file, which we'll see now. And this is the style file for the HTML file. Now to run the project, simply you just need to right click here and then click on open with live server, and the project will automatically run the live server. Says this is basically an easier way instead of running it on C++ and it used to use a web-based browser. So for the script, this is the script. We had a few things here. First of all, we need the flag to the flag. If it's one or boolean, it's basically boolean. If it's true or false. And then we have the turn to determine which turn it is. And then we have the state to show the state here, as you can see. And then we also have the queue to denote the queue, and then we have the critical if it's false. This is basically to update the UI and get the process, this part. And then here we actually do the reset here we do the reset to reset the algorithm. Once you click on the reset button, the algorithm will basically reset right away. And then this is actually just to know the start process, which is only allowed starting if the process is idle. And then basically, here we have the queue. We have the step 1, step 2, step 3 with explanation as well. And then for the final step, which is basically going to be the exit section. And here, basically, the last step is going to return us to the ideal state. And in the end, this is basically this function is basically meant to prioritize the process 0, then 1. And at the end here, as you can see, this is the reset. So once you do anything here and then refresh the page, it will get back again to its normal default settings. All right, so I guess for my part, this is the data structure. It's basically all of this is mentioned in the JavaScript file. Okay, we don't already talked about them. So now move to Wafi to describe the more for the front end. So I will turn off my screen share and let Wafi do its own. Okay, Wafi. Yeah, we can see your screen. Wafi, your mic is off.
Okay, so I will do the project demonstration. So first, as you can see, so first I will just reset first. Okay, at the explanation, you can see that it says click start process 0 or start process 1 to begin. Step 2 the algorithm to see how this algorithm ensures mutual exclusion. So I will choose to start process 0. So when I start it, it will say that this process 0 is trying. Okay, then I will press the step button. Then it said that flag 0 true, the process 0 wants to enter. Then it says, when I step it again, it says that turn is process 1. Then I step again. process 0, it says that waiting for other process, which is process 1, either to leave or give up turn. As you can see here, at flag 1, false, means that process 1 does not want to enter the critical section, even though it is its turn. So, after this, when I step again, process 0 will enter critical section. Here, as you can see, critical section, process 0. Okay, but what if when the process 0 is in the critical section, what if process 1 also want to enter the critical section? So if I press start process 1, it says that process 1 trying to enter critical section. Then when I press step, it says that process 0 exiting critical section. It means that for process 1 to enter the critical section, process 0 must exit the critical section first. So then when I step again, so it says process 0 back to idle. And there is no process in the critical section. When I step again, flag 1 wants to enter, which means process 1 want to enter. Turn 0 and waiting for other process to leave or give up turn means that process 1 will wait if process 0 want to enter the critical section, because as you can see here, the turn is for process 0. But from the flag, we can see that process 0 does not want to enter the critical section. So process 1 will enter here. Process 1 is in the critical section. Then process 1 will exit, and then both process will go back to idle. So I think that's all for the demonstration.
Okay, thank you so much, Wafi, for your explanation.
So I will stop.
Yeah, I will go back to my present to present the rest. We're gonna talk
Yeah.
about the results and discussion. So basically, as you guys saw from the results, it basically successfully demonstrate the Bedrooms algorithms with the risk conditions between two proceeds, process 1 and process 0 as well. A temperature toggle and share light switch. When both threads tries to enter the critical section simultaneously, the algorithm allowed only one process proceed while the other waited. Now we're gonna talk about the performing the test, such as one process starting before the others. Simulation will allow the first process to enter the critical section, and then basically the consequent process will have to wait until the first process. For both cases starting at the same time, the simulation will allow, as we said again, only one of the processes, which is going to be preferable P0, into the critical section first, while P1 will wait until the P0 leaves, as Wafi showed us before. Now, for the discussion part, um, we have actually discussed about a few things, but to observe all these results, we showcase the strength and outcome of Patron's algorithms, and also the simulation provided a clear visual understanding of how process converted without hardware-based mechanism like Semospheres or mutexes. Also, we make sure that it's a browser-based, since if we did it in C++ or other language, it's going to be harder to showcase or run, since we need the console log. The browser-based version make it easy to observe and understand the behavior of the algorithm. Okay, now here's the future work part. Things that we might think is going to be better if we did it in the future. Adding the auto step or run mode is going to be simple. Add a button that will let the simulation run automatically without advanced steps every second. User have no need to click the steps button manually every time. Also, we can show what happened without the algorithm. Include a mode where Python's algorithm can be turned off purposely to let both processes run freely to show how risk condition can happen when both processes runs. This is to show the problems that Python's algorithm solves. And then we have better visual feedback for waiting. That's just a comment. And then highlights the code as it run. And then basically finally the contributional performance tracking to show how many steps took by each process to enter and how many times they were forced to give a sense. So that's it for our project. This is the conclusion as well. We have successfully managed to show it in a simpler way using HTML, CSS, and JavaScript, basically an everyday web technology. That's it for our team. Assalamu alaikum warahmatullahi wabarakatuh.